Let's continue. These are the limitations of YOLO. First is each grid cell predict only 2 bounding boxes, so there is the limit of a number of nearby objects that can be accurately detected. Also, it was difficult to detect small objects since YOLO struggles with detecting small objects that appear in clusters. Also, another limitation is reliance on coarse features. YOLO employs multiple downsampling layers, resulting in the use of relatively coarse features for predicting bounding boxes, potentially affecting localization accuracy. So the main basic problem of YOLO, first YOLO version was detecting localization errors. And these are the results of YOLO. On Pascal VOC dataset compared to other real-time object detectors. As we can see, YOLO getting the highest accuracy, and also there is fast YOLO, which get lower accuracy but get much faster speed. And there is error analysis of fast RCNN and YOLO. And as we can see, YOLO have the a lot of errors, localization errors. So, and second version of YOLO was published in 2017, and the author said it was better, faster, and stronger than first version of YOLO. And there is also called YOLO 9000 because of it can detect 9,000 class labels. So it's actually first version of YOLO added with a lot of number of improvements. So first part is better to improve accuracy of the YOLO. First improvement was batch normalization. This was to increase convergence and provide regularizer to avoid overfitting. It was used to all convolutional layer. And the second improvement is high resolution classifier. As we said earlier, YOLO was pre-trained on ImageNet, but with the 224 to 224 input size. But in the second version of YOLO, it was trained directly from 448 to 448, and the object detection was used on the same input size. Also, they removed fully connected layer from architecture and used only convolutional architecture. And another thing they used in version 2 is they used anchor boxes. Like in first YOLO, they didn't use anchor boxes, but in the second version of YOLO, they defined anchor boxes and made an algorithm that predict the coordinates and class for each anchor box. The number of anchor boxes determine the size of the network output. And they use dimension clusters. They use K-mean clustering on training bounding boxes to find most optimal priors. By testing different number of K, they found 5 as most optimal for model complexity and higher recall. And they also used fine-grained features. So they changed the they changed the input size to 416 to 416 to achieve 13 to 13 grid output feature map, and this was to make grid the odd number of sizes, like 13 to 13, not 14 to 14 in case of 448 to 248. And so in the and there is so this fine-grained feature means in the middle of convolutional layers with the size 26 to 26, they get the feature map and stack nearby into our final feature map. So there is, and the resultant feature map is concatenated with the lower resolution. So it's basically, it takes two resolutions, higher resolution and lower resolution, and concatenates them. And also multi-scale features. Yolo version 2 does not fully connected layers, so inputs can be of different sizes. So deal with this. They trained on random input sizes every 10 batches. And the input size was between 320 to 608. This is the results of Yolo version 2. Here we can see frames per second to mean average precision graph compared to previous other methods, other object detectors. As we can see, compared to first YOLO version, it's get higher accuracy and better FPS. Here's the line is detect real time. So here we can see other not real-time object detectors, which can maybe get similar or less accuracy compared to YOLO version 2. And the YOLO version 2 was also tested on Pascal VOC. And this is all the improvements made from YOLO to YOLO version 2, and listed. As we can see, by adding all these improvements, we get much higher accuracy compared to YOLO version 1. So each improvement add a little bit of improvements. And the second part is faster. They changed the architecture to darknet 19, and it only requires 6 billion operation to process an image, yet achieves 73% top 1 accuracy and 91.2% top 5 accuracy on ImageNet. So darknet CNN looks like this. Like, as we can see, there is no fully connected layers. They changed all to convolutional layers. And another thing that YOLO version 2 added is YOLO 9000. It basically it combined a dataset using word tree hierarchy so that it will be able to classify 9,000 labels. It merged such that when merged both ImageNet and the object detection COCO dataset, so that when we get the ImageNet dataset, they update the classification part, and when we get the COCO dataset, they update the object detection part. And the next version is Yolo V3. It was published in CPR 2018. Here is the result of Yolo version 3. As you can see, it achieves very fast inference time while getting comparably good accuracy. Yolo version 3 also adds improvements to previous versions. First, it was similar to previous Yolo version 2, and they used bounding box prediction. And in Yolo version 2, closest bounding box to ground truths get 1 score, while others get assigned with 0 score. And in case of not assigning anchor box to any object, only classification loss was calculated. And for class prediction, Yolo version 3 used binary cross entropy to train an independent logistic classifier. It was to address the problem as multi-level classification, and they was used instead of softmax for the classification. It was used to assign multiple labels to the same box. Also, architecture was changed. Backbone network was changed from Darknet 19 to Darknet 53. Darknet 53 was composed of 53 convolutional layers with residual connections, and there was no pooling. There was no pooling layers. Similar to Yolo version 2, they used multi-scale predictions. They predicted three boxes at 3 different scales, and at the end combined their features to get more accurate classification. In Yolo version 2, there was used 5 prior boxes per cell, while in Yolo version 3, there was 3 prior boxes for 3 different scales. They also used like anchor boxes. It's Darknet 53. It consists of 53 convolutional layers, and there is no pooling layers. Pooling layers was changed to convolutional layers.
So your speed is better than previous version.
Yeah.
But how would they achieve that? Because it seems their architecture is more complex. And how would they achieve less speed?
How they achieve speed? I think maybe yeah. I think maybe here we can see. So maybe it's not faster. I think I didn't see any like comparison with Yolo 2 with
Maybe slower.
yeah. And this is like how multi-scale detection architecture works. So basically it get branched into 3 different outputs, and at the end they each of for the like 3 different resolutions, and the final predictables are filtered using non-maximum suppression. So it basically get simply like neck part of the object detectors. So it gets three at three different scales, and for three different scale they get they use three anchor boxes. And this result comparison, like accuracy comparison with other object detectors. As we can see, it's get very good, very very good accuracy, but it's get lower accuracy than RetinaNet. But it's worth keep in mind that RetinaNet has like 3.8 longer time to process an image. There's other experiment results. So as we can see, inference time of Yolo V3 much better than compared to RetinaNet, and get comparably good results. So the modern object detectors can describe as backbone, neck, and head. And next is Yolo version 4, optimal speed, accuracy, and accuracy of object detection. Authors described like two kind of improvements in this paper. First is back of freebys and the back of specials. Back of freebys are improvements that are not affecting inference time, but increasing the accuracy. And the second is back of specials, which are improvements that may be slightly increase the inference time, but improve accuracy a lot. So there are back of freebys used in Yolo version 4. It's data augmentation. They use a lot of simple data augmentation techniques like brightness, contrast, scaling, cropping, flipping, rotation, but also introduced their own mosaic augmentation. It basically combines 4 images into a single one image. It allows outside of primitive context and reduce need for a large mini batch size. Another improvement is regularization. Drop block as a replacement for dropout. It helps with overfitting. Also, for detector, they use CIO plus, which considers the overlapping area and distance between center points and aspect ratio in bounding box regression. Also, they changed batch normalization to cross mini batch normalization. Cross mini batch normalization takes statistics from the full batch rather than individual mini batches, which can enhance the model stability and performance. So it basically like get the statistics from all the previous branches rather than only individual batch. And the architecture of Yolo version 3 was like composed of 3 parts: backbone, neck, and head. So backbone was similar to Yolo version 3, used darknet 53. However, in Yolo version 3, it was enhanced with cross-stage partial connections, CSPnet, and also activation function was used in Yolo version 3 is mesh, not the traditional ReLU function. Yolo version 3 does not include the feature pyramid network used in Yolo version 3. Instead, it modifies the like there was also Yolo version 3 SPP version of Yolo, so it incorporates a modified version of this feature pyramid network. Also, Yolo version 3 introduced a modified version of the path segregation network, which concatenates features instead of adding them. So it add it in PANet, in original PANet, they add the features, but instead YOLO version 3 concatenates them. And for the head, YOLO version 4 detection head is similar to YOLO version 3. So they use the same head for the same head as YOLO version 3. So the total model look like CSP darknet and modified PANet and the YOLO version 3 head. So it's architecture for the object detection in YOLO version 3. And there is backup specials that was used in YOLO version 4. First is mesh activation with SPP and PANet. Mesh activation function provides smoother gradient and utilized along with the SPP and PANet architecture to improve performance. So as said, backup specials are like improvements, like to get better performance, but can be more computationally expensive. Also, cross-iteration batch normalization, techniques that leverage the statistic from multiple iterations of the model during training to enhance the normalization process. And all the all the improvements based on architecture are related to these backup specials. So it slightly increase the computational time, but get higher accuracy. Also, I/O loss correction was changed. In addition to the I/O loss, YOLO version 3 introduced the intersection over union loss and the correction mechanism to better handle overlapping objects and improve localization accuracy. Like this experiment results of YOLO version 3 compared to other object detectors. So the left, this is frames per second to API graph, and the left part is right part is real-time object detectors. So as we can see, YOLO version 3 is getting yeah, I think it's too small.
So please don't make presentation PowerPoint like this. You cannot don't include pictures, figures, whose text is too small.
Yeah.
So please divide the figures there.
Yeah. So, yeah. But basically, like this are the YOLO version 4. So as we can see in real time compared with other real-time object detectors, it gets the highest accuracy. And also like starting from YOLO version 3, it was used Coco dataset instead of Pascal VOC.
By using Coco.
Uh,
By using Coco.
yeah.
Was there any
I think like in Coco dataset there are more like class level. Yeah.
Pascal is
80. Yeah. Yeah, like and from I think from YOLO version 3 they only use like Coco dataset starting from